Hello, my name is Professor Shannon Betcher here at the Oregon Center for Electrochemistry. This is the first lecture in a series focused on the fundamental aspects of electrochemistry. In this lecture, I'll discuss some of the general features of electrochemistry, its history, and some of the exciting applications in this area. Electrochemistry is simply the flow of electrons and ions to cause chemical change, or the reverse. Chemical change can cause the flow of electrons and ions to give, for example, energy in a battery. It involves the movement of both electrons and ions. This is particularly important if you think about an electrode, say a metal, and a solution. If I have an electron in the metal and I transfer into the solution, there's going to need to be some movement of ionic charge to compensate that electronic charge that moves. Typically, we have both a cathode, where the reduction reaction takes place. Reduction, remember, is transfer electrons onto a species. And anode, where an oxidation happens. Oxidation is removing electrons. And then we have an electrolyte to move ionic charge. And we'll go through some of the more rigorous definitions in this course. There's a number of important applications that I'd like to summarize. Before I get there, though, I'd like to talk about some of the history or historical aspects of electrochemistry. I'll just highlight a few really key discoveries that set electrochemistry on its course and were actually critical to all of science. Okay, so Alessandro Volta, in fact, invented the first practical electrochemical system, the voltaic pile, named after him, and the volt, in 1800. Now, the voltaic pile consists of a stack of alternating metal plates of different composition. One of them being a reactive metal like zinc, and one of them being a less reactive metal like copper or silver. Now, Volta, in fact, built this system to challenge one of his colleagues, Luigi Galvani's claim. And Galvani believed that he had discovered something called animal electricity. This idea that animals can produce electricity like lightning or anything like that folks at this time in history were really interested in understanding. And so what Galvani showed is that when he took two metal leads and he attached them to a frog leg, he could get an electrical response, okay? And actually the leg could be moved. And that this was his proof that animals produced electricity. But his results, Galvani's results, came from using two dissimilar metals. For example, zinc and copper, connected by an ionic conductor, so a material, an electrolyte that conducts ions, and that is the frog's leg. And so what Volta did is he actually invented the battery to show that you could get electricity from a purely artificial system. So that the animal, the nature, the soul of the animal was not involved in the electrical response. This was incredibly important, and Humphrey Davy is another key figure here. He was an English chemist, and he was the one to really link the electricity that was generated with chemistry. And this is in the 1806. This is one of his key publications, but sort of the early 19th century. So he realized that the production of electricity by the voltaic pile, these stacks of different metals, depended on chemical reactions, depended on chemical changes to the metal, not just the contact of different metals. So it wasn't a physical process of contact, it was actually a chemical process. There were chemical reactions going on. And now, of course, we understand those chemical reactions to be oxidation reduction reactions, redox reactions. And he used the current supplied by the voltaic pile to separate compounds into their parts. And he discovered all these elements. So he purified and discovered sodium, potassium, calcium, magnesium, strontium, and barium. This is remarkable. So this is one scientist discovered 6 new elements and isolated them and measured their properties. He also correctly identified the composition of chlorine made from electrolysis, sodium chloride. So if you electrolyze sodium chloride, you get sodium metal at one end. If you go to very negative potentials, a big voltaic pile, and you can actually evolve chlorine gas at the other. And another key interesting side note is he actually invented a very important technology that's still in use today called cathodic protection. This is a way to actually prevent corrosion, prevent rusting of metals. So we'll talk about this in a moment in more detail, but rust forms when a metal gets oxidized. So if you can prevent a metal from getting oxidized, you can prevent it from rusting. And what he figured out is that if he bolted on a very reactive metal like zinc onto the hull of a ship that was iron or copper, the zinc would get preferentially oxidized. It's much easier to oxidize the zinc than iron or copper, and that would actually prevent the hull of the ship from getting oxidized. And we'll talk about how that works through the course later. Now, Michael Faraday was Humphrey's student, and turned out to be one of the most influential scientists in history. He was able to link magnetism and electricity, and he used this to invent the electric motor, to invent the dynamo. Dynamo is basically an electric motor running in reverse, converting mechanical motion into electricity. And what he did is he showed that this magnetoelectricity is the same, has the same chemical effects as electricity generated by this voltaic pile, which was this chemical redox reaction. He also proposed Faraday's law, and we now have a constant named after him, the Faraday, 96485 coulombs per mole. So it's the number of electrons in a mole of electrons, number of coulombs in a mole of electrons, sorry. And it relates the amount of current past the quantity of material electrolyzed. So if you electrolyze 1 mole of sodium plus, right, to sodium metal, you'll have to consume 96485 coulombs, okay? And a coulomb is a measure of charge. He also invented the modern system of oxidation number. So now I want to take a few moments and talk about some examples from modern electrochemistry that are very critical to technology and to our modern lives. The first, I think, is perhaps right now one of the key advances that is enabling clean technology, enabling our ability to switch from a fossil fuels based economy to one based on clean renewable electron energy. So if I think about a battery, and a lithium ion battery, it has, again, 3 parts. So it has a cathode, an anode, and a separator, electrolyte, right? And the way this works is you have lithium in the charge state, lithium 0, intercalated in between the 2-dimensional sheets of graphite. So graphite's made of these sheets stacked upon each other, and the lithium is actually able to move in and out of those sheets. And when you charge a lithium ion battery, you put lithium plus in, and you put an electron on that lithium plus, and you get lithium 0, nominally lithium 0, okay? And on the other side, the cathode, you have lithium sitting interstitially in an oxide. This is an iron phosphate cathode. There's a number, nickel cobalt oxide, variety of cathodes used. Those lithiums are essentially lithium plus, nominally lithium plus 1. Okay, so when you charge a battery, you pull lithium plus out of this side, and you put lithium plus in on this side. So you have lithium 0, and you have an empty spot over here left over. And to do that takes energy, right? Because you're taking lithium plus, which is sort of how you normally find lithium in the environment in its oxidized state. And you're essentially taking the electron that was on a transition metal, in this case an iron, you're pulling that electron out, you're pumping it up to higher energy, and you're putting it on a lithium metal. And that lithium metal is very reactive. Now, when you want to discharge your battery, you do the reverse reaction, right? So you pull the electron back off of the lithium. It can go and do work. It can do work externally, electrical work in the external circuit, and get recombined with the cathode, reducing the iron back to a lower oxidation state and intercalating a lithium plus to compensate that charge. So this is a rechargeable, reversible process. So the basic idea then is that lithium ions have different energies, different charge states at different electrodes, the anode versus the cathode, leading to a cell potential. And we want to design batteries that last longer, so we need to understand all these electrochemical processes. We want to store more lithiums per kilogram. We want a higher density of energy storage, so that involves designing new materials for the anode, the cathode, the separator, the electrolyte. We want them to be safer, so we'd like to figure out how to get electrolytes that conduct lithium very well, but are not flammable. So water-based electrolytes are very exciting in the recent academic literature. And we'd like them to charge very fast. So the electrochemical kinetics of moving ions and moving electrons is very, very important. Let's go on now to another example that's close to my heart, and that's water electrolysis. So water electrolysis, that's the overall reaction here, taking water and splitting it into hydrogen and oxygen. And you can do this with electricity. So this is an uphill reaction. So this has a positive delta G, right? So it's not a spontaneous reaction. So we have to put energy in. So we do electrical work. And we do electrical work by applying a voltage and driving electrons into the cathode at high energies. And those electrons combine with protons to make hydrogen. Now at the anode, we have to get those electrons from somewhere. Those electrons come from pulling electrons off water. And when you do that, you generate protons and you generate oxygen, as given here by the balanced equation. So this is, in principle, a very simple device, but it turns out engineering and building these three-dimensional regions where all this chemistry takes place is in fact quite challenging, especially trying to get that to operate at very high efficiency. So there's a number of challenges here. So one of the things we'd like to do is decrease the loss in these electrolysis systems. And so you can quantify it this way. So there's a value called the thermoneutral voltage. It has to do with the thermodynamics for these reactions. And it's about 1.4, a little over 1.4 volts. And the overall cell, however, requires substantially more voltage than the thermoneutral voltage. So if you want to run the cell, for example, at 3 amps per centimeter squared, you need over 2 volts. And the thermoneutral voltage, if there were no losses, would only be about 1.45 volts. Okay. And so there's different types of losses associated with the different processes going on in this cell. So one of them is called activation losses, and that's actually the losses associated with transferring the electrons. So these are electrochemical kinetics. We'll talk in great deal about electrochemical kinetics and how this works. And iridium oxide actually is the active material. It's a catalyst for this reaction, so it speeds up this water oxidation reaction, but there's still a substantial loss due to water oxidation. The other loss that is important is the ohmic loss. Protonic ohmic losses means the voltage loss driving the protons through this membrane. Okay, so this membrane is essentially a resistor, like in general physics, you learn about V equals IR, the current flowing through a resistor is related to the driving force, which is the voltage. And in this case, you're moving protons, and again, you have a linear dependence on the cell voltage as a function of current density. So there's a loss here in driving large voltages. There's other losses, for example, electrical ohmic losses. Those are moving the electrons. Mass transport, that means moving the oxygen and things like that. So we'll talk about these in some detail. These are exciting because hydrogen, the product of this reaction, is really a viable fuel for long-distance transportation, shipping, aviation, freight. It's an exceptionally good fuel for long-term energy storage, which is something that batteries are particularly not good at. They're too heavy for long-distance shipping. They're good for light transport, short-distance transport, but not particularly good, for example, if you want to take a ship from a port in China to LA. So the inverse of a water electrolysis system or device is called a fuel cell. Fuel cells take fuel, hydrogen and oxygen, this is a hydrogen fuel cell example, and put out electric power. They're able to do electric work. And they were first invented by Grove, actually quite a while ago, 1839. And he called this a wet cell or a gas battery because he could, electrolyze water, generating hydrogen and oxygen, and then he could recombine that hydrogen and oxygen and get the chemical energy of the hydrogen oxygen back out as electrical work. And the first really practical and operational fuel cell has been attributed to Francis Bacon in the 40s. And how this works is basically you have an anode. It's essentially the reverse of the electrolyzer I showed you. You have an anode where H2 comes in and is oxidized to make protons, H plus, and electrons. Now those electrons are high energy electrons. You can pass them through an external circuit and get work out, and then put them into the cathode where they can react with oxygen, which really wants electrons. So it's a spontaneous reaction for the electrons in hydrogen to move to oxygen. And what we're doing is we're pulling the electrical work out of those electrons. And now the protons have to move across the membrane, going from the anode to the cathode. And so the electrolyte is something called naphthalene. This is naphthalene. It's basically a strong acid. These are sulfuric acid groups, sulfonic acid groups. It's basically a strong acid like sulfuric acid on a fluorocarbon polymer. So it's essentially a solid acid. So these are very exciting because you can basically get electricity efficiently, cleanly from hydrogen and air. There's many industrial processes that depend on electrochemistry. For example, electroplating. So many electronic circuits, electronic components are electroplated or made by electroplating. Jewelry is often electroplated. You could imagine having an anode, and if I pull electron off of copper metal, I'll make copper 2+, right? I can pull the electrons off. I can push those electrons up in energy, put them on another metal, and take copper 2+ in solution and coat that other metal with copper metal. So I can build a plated thin film, and this is useful for protecting the surfaces or endowing a metal or plastic even with the properties of a thin film of a more expensive metal. So this is used quite often for that. It's actually used in the manufacture of CPUs. They use the electrodeposition to deposit the interconnects that connect all the components of the CPU together. Another thing that electrochemistry is used for is actually making elements. So aluminum, this is aluminum metal manufacture. It's a high temperature process. You take molten aluminum oxide. Molten aluminum oxide is in the electrolyte. It's an ionic conductor. And you have carbon anode and cathode. The cathode reduces the aluminum 3+ to aluminum 0. And that aluminum 0 is metallic and molten and can be flown out of the bottom of the electrolyzer. Before this process was developed, aluminum was actually one of the most expensive metals around, and now it's incredibly cheap due to this electrochemical process. Corrosion, we mentioned this earlier, is something that costs the world tremendously in terms of degradation of infrastructure. Here's a picture of a ship. This is the SS Mahano. It crashed on Fraser Island off of Australia. And, over time, you see this reddish brown color developing on the skeleton of this wreck. And that reddish brown color is, of course, rust. And rust is typically iron oxides or oxyhydroxides. And corrosion occurs due to oxidation of a metal. In this case, iron's oxidized to form iron 2+, which can combine with oxygen and water to make these rusts, which precipitate and make these scales on the surface. Now, the interesting thing about corrosion is because this is a metal that conducts electrons, the electrons that come from the iron don't need to react with, for example, oxygen at that site. They can move to another part of the metal and react with oxygen. So how this, why this is interesting is because what Humphrey Davy showed is if I put a piece of zinc here, I can prevent this from happening because I can take the electrons. So the oxygen is what is eventually doing the oxidation, right? The oxygen is what's taking the electrons from iron to make the rust. Now, if zinc is much easier to oxidize than iron, I can take those electrons and I can put those electrons, take them from zinc instead of taking them from iron because it's easier to get them from zinc, and I can consume all the oxygen. So basically the zinc is getting oxidized preferentially and taking and consuming all the oxygen. Even though the zinc is only in one spot, the electrons can move everywhere in the metal. So I wanted to end with a couple examples from biology. One is medical sensing of glucose. So if you're diabetic, you will carry a glucose sensor that allows you to very quickly and easily measure your blood glucose levels. Of course, if you're diabetic, your body has trouble regulating those levels, and you need to be very careful to make sure they stay within a well-defined range. And so how these work is really quite interesting. So they're electrodes, and they oxidize the glucose, okay? But the problem is you have in blood, you have all sorts of different things that can be oxidized. So how do you selectively just oxidize the glucose? And so this was developed by a very famous electrochemist named Adam Heller. And what he figured out is he could take an enzyme, I believe this is glucose oxidase, so it's an enzyme that selectively binds glucose and oxidizes it, pulls the electrons off of glucose. He could use that enzyme and wire it into a sensor. And so how do you do that? Well, he embedded that enzyme inside of a polymer. So this is a polymer, see these N, it's the repeating units of the polymer. And this particular polymer has an osmium N group. And this osmium can be in different redox states, different oxidation reduction states. And so electrons can actually hop from osmium to osmium through this polymer. And if you embed this protein, this enzyme, inside of a film of this redox active polymer, it actually electronically wires this biological active site to, for example, a carbon working electrode. And using this, you can selectively oxidize glucose and get a current from that oxidation that's proportional to the glucose concentration in blood. The last example I want to talk about is membrane potentials in biology. We'll talk more about this in more fundamental detail. But imagine you have a cell membrane, okay? Cell membrane has these phospholipids that prevent mixing of the left side and the right side of the extracellular liquid and the intracellular liquid or solution. And it turns out inside of cells, there's a much higher potassium concentration than outside of cells. Now, if you have proteins that sit in this cell membrane wall that form ion channels, and those ion channels can be quite selective, for example, for potassium. So in this case, potassium can go back and forth from these two solutions, but other ions can't. Anions can't. Anions are too large in this example to get through this ion channel. And so what happens is, because the concentration is large on this side and small on this side, potassium wants to go across the membrane through this ion channel. And it does to some extent. But the problem is it can't pull across the anions. And so what happens is an electrostatic potential, a voltage builds up across that cell wall. So this is the origin of membrane potentials in biology. They're incredibly important to the function of physiology, how life functions is one example. Here's a nerve, and this is a terminal, a presynaptic terminal between the heads of two nerves. And how signals are transduced is basically by generating and collapsing these membrane potentials via neurotransmitters. And so electrochemistry is intimately involved in how the brain transmits signals throughout the body and how it records signals. And there's a lot of excitement right now in sort of interfacing and measuring signals in the brain and in nerves and inducing signals using electrical circuits. Okay, so with that, I'd like to now sort of get to the meat of electrochemistry. So that was sort of the excitement. And now I want to talk a little bit about, what are the pillars of electrochemistry that we're going to cover in this course. And there's really three, okay? Three pillars of electrochemistry. One is electrochemical thermodynamics. And thermodynamics is a science that tells you what is the equilibrium state of a system, and how do we calculate that and understand that? And then how do we figure out what the driving forces are for a system to reach equilibrium, okay, that may not be in equilibrium. But it doesn't tell us anything about how fast the system reaches equilibrium. Another pillar is electrochemical kinetics. So electrochemical kinetics tells us how fast processes happen. For example, if I have a bunch of electrons and I have, say, a bunch of aluminum, right, to take our example, 3 plus, how fast do those electrons transfer? What's the rate constant for electron transfer there? And so there's a whole theory which we'll go through in much detail that allows us to understand and calculate electron transfer rates. And then the third pillar is transport. And this is something that chemists don't typically learn very well as undergraduates, though chemical engineers get a lot of, and that's how do species move? And that's really important in an electrochemical cell because ions are moving, electrons are moving, solution is moving often, and so movement is generally via 3 mechanisms: diffusion from high concentrations to low concentrations. Migration is the effect of an electric field, electric potential on charged species, and convection is the sort of the flow of species. And so what we'll do in this course is we'll go through these in some detail after we give a sort of an overview of electrochemistry and talk about cells and various aspects that allow you to get a bigger picture understanding. We're going to talk about each one of these 3 in some detail before then going on to a few more applications. So I'm really excited to be working with you this term, and I'm looking forward to going through this really exciting material with you. Thank you.